124 light-years from Earth, a world exists that shouldn't be possible. Scientists detected something in its atmosphere that, on our planet, only comes from life. Not ancient fossils. Not chemical traces buried in rock. An active signal, present right now, floating in alien skies above an ocean that might stretch deeper than anything in our solar system. K2-18b orbits a dim red star in the constellation Leo, receiving about the same amount of light Earth gets from our Sun. But that's where the similarities end. This planet is more than 8 times Earth's mass and nearly 3 times wider. Its density falls somewhere between our rocky world and the ice giants lurking in the outer solar system. The James Webb Space Telescope aimed its instruments at this distant sphere and found water vapor, methane, carbon dioxide. Then it detected something else. Dimethyl sulfide. A molecule that, as far as we know, only biological processes produce. The scientific community is divided. Some researchers call it the most promising biosignature ever detected beyond Earth. Others point to recent laboratory experiments showing that non-living chemistry might create the same signal. Both groups agree on one thing. We're looking at a type of world that has no equivalent in our solar system, and we're only beginning to understand what it actually is. K2-18b belongs to a class of planets called subneptunes. They're the most common type of planet we've found orbiting other stars, yet we have nothing like them circling our Sun. Too large to be rocky like Earth or Mars. Too small to be gas giants like Jupiter or Saturn. These in-between worlds dominate the galaxy, and until recently, we had no idea what their surfaces might look like. The star K2-18 is what astronomers call an M-dwarf. A red dwarf. Cooler than our Sun by more than 2,000 degrees Celsius. Smaller, with only 45% of our star's radius. From Earth, even with the most powerful telescopes, you can't see it without instruments. It's simply too dim. Yet this unremarkable star, one of trillions like it scattered across the Milky Way, might be hosting something extraordinary. Red dwarfs make up roughly 75 to 80% of all stars in the galaxy. They burn their fuel so slowly that none of them, not a single one born since the universe began, has yet died of old age. K2-18 is estimated to be around 2.4 billion years old. Young by stellar standards. Our Sun is more than twice that age. But even at this relatively early stage, K2-18 has already settled into the calm, steady burn that will continue for hundreds of billions of years. The planet completes one orbit every 33 days. Fast by Earth standards, but this places K2-18b squarely in what scientists call the habitable zone. The distance from a star where temperatures allow liquid water to exist on a planet's surface. Not too hot. Not too cold. The Goldilocks zone, as it's often called, though that nickname hides how complex habitability actually is. When the Kepler Space Telescope first spotted K2-18b in 2015, it was just another data point. A slight dimming of starlight as an object passed in front of its host star. Thousands of such signals were being catalogued. What made this one different emerged later, when scientists calculated the planet's size, mass, and position. Here was a world in the habitable zone, large enough to hold onto a thick atmosphere, but potentially small enough to have a solid surface beneath. Then came the atmosphere measurements. The Hubble Space Telescope detected water vapor in 2019. Not just traces. Significant amounts. But Hubble's instruments couldn't tell us much more. its sensitivity had limits. The wavelengths it could observe were restricted. Scientists knew there was water, but they couldn't see the full picture. They needed something more powerful. The James Webb Space Telescope changed everything. Launched in late 2021, Webb's mirror is nearly 3 times wider than Hubble's. Its instruments operate in infrared wavelengths that Hubble can barely touch. When Webb observed K2-18b, it needed just 2 transits to gather data that would have taken Hubble years of observations to match. And what Webb saw transformed K2-18b from an interesting discovery into something that might rewrite our understanding of where life can exist. The spectrum showed methane, about 1% of the atmosphere. Carbon dioxide, also around 1%. Water vapor, though less than 0.1% in the upper atmosphere where Webb's instruments are most sensitive. This combination is strange. If K2-18b were just a small version of Neptune, we'd expect to see ammonia. Lots of it. But there's barely any ammonia at all. The absence of something can be just as revealing as its presence. Scientists proposed an explanation that sounds like science fiction. K2-18b might be a Hycean planet. The term combines hydrogen and ocean. Picture this. A rocky core, possibly similar in composition to Earth's. Above it, an ocean. Not like our oceans. Deeper. Much deeper. Potentially hundreds of kilometers deep, stretching across the entire planet. And above that ocean, a thick atmosphere of hydrogen and other gases, pressing down with immense weight. Niku Madhusudhan at the University of Cambridge coined the term Hycean in 2021. His team realized that planets like K2-18b could maintain liquid water oceans despite having hydrogen atmospheres. Conventional wisdom said such worlds would be too hot. The hydrogen would trap heat, creating runaway greenhouse effects. But the models showed something different. Under the right conditions, with the right distance from the star, these worlds could stay cool enough. The hydrogen blanket wouldn't cook the ocean. It would protect it. This hypothesis explains the atmospheric chemistry Webb detected. An ocean world with a hydrogen atmosphere would have methane and carbon dioxide from biological or geological processes in the water. The hydrogen would react with oxygen, keeping oxygen levels low and preventing ammonia from accumulating. Everything fits. Almost too neatly. Then there's the dimethyl sulfide, DMS, as scientists abbreviate it. On Earth, this molecule comes from phytoplankton, microscopic marine organisms that drift through our oceans by the trillions. When they metabolize certain compounds, they release DMS as a waste product. It rises from the ocean into our atmosphere. You can smell it at the beach sometimes. That distinctive ocean scent. That's partly DMS. We've never found a non-biological process on Earth that produces meaningful amounts of DMS. It's considered one of the most reliable biosignatures we know. So when Webb's data suggested DMS in K2-18b's atmosphere, the implications were staggering. But here's where it gets complicated. The signal isn't strong. Statistically, it's at about 2.7 sigma confidence. In particle physics, scientists don't announce a discovery until they reach 5 sigma. That's a standard that means there's only a 0.00006% chance the signal is just random noise. K2-18b's DMS signal has about a 0.3% chance of being statistical fluctuation. Not terrible, but not conclusive either. More troubling, laboratory experiments in 2024 showed that certain chemical reactions in hydrogen-rich atmospheres can create DMS without biology. Ultraviolet light hitting specific molecules. Chemical pathways we hadn't considered. And in 2024, scientists detected DMS on a comet. A cold, lifeless comet. Suddenly, this supposedly bulletproof biosignature had holes in it. The debate intensified when researchers realized other molecules could be mimicking the DMS signal. Hydrocarbons with similar spectral signatures. Compounds that would look like DMS to Webb's instruments but mean something entirely different. Confirming what's actually there will require more observations. Different instruments. Years of additional data. Some scientists argue K2-18b isn't a water world at all. Recent computer models from September 2025 suggest that in planets this size, chemical processes destroy most water molecules. The hydrogen and oxygen separate. They bond with metals and other elements, sinking into the planet's interior. What looks like a water world from the outside might actually be a gas-rich mini-Neptune with no ocean at all. Just a thick, crushing atmosphere surrounding a core of rock and metal. The alternative interpretation is darker. Instead of a life-bearing ocean, K2-18b could have a surface of molten magma. The hydrogen atmosphere would trap heat efficiently. Too efficiently. The planet would be an inferno beneath its cloudy skies. The atmospheric chemistry we're seeing wouldn't come from life, but from volcanism. From the planet's interior bleeding gases into the sky. Both models fit the data. Both explain what Webb observed. The water world hypothesis needs life to account for the methane levels. The gas-rich model doesn't. Occam's razor suggests we should favor the simpler explanation. But simpler doesn't always mean correct. What makes this so difficult is that K2-18b exists in a category we don't fully understand. Subneptunes have no analog in our solar system. We can't visit one. Can't send a probe. Can't study one up close. Everything we know comes from analyzing starlight that's traveled for over a century through space, passed through an alien atmosphere for a fraction of a second, and then traveled another century to reach our telescopes. We're reading fingerprints in that light. Chemical signatures. Trying to reconstruct an entire world from shadows and spectra. The planet's density offers clues but no certainty. At 2.67 grams per cubic centimeter, it falls between Earth's 5.51 and Neptune's 1.64. That's consistent with a rocky core and thick atmosphere. It's also consistent with a water-rich composition, or an ice-rich interior with a moderate atmosphere. The density alone can't tell us which. The amount of light K2-18b receives is eerily similar to Earth's. About 1,368 watts per square meter, give or take. But that doesn't guarantee habitability. Venus receives almost twice that much, and its surface is hot enough to melt lead. Mars receives less than half, and its surface is a frozen desert. The amount of light matters. But so does the atmosphere. So does the planet's ability to regulate its temperature. So does whether there's even a surface to stand on. Understanding K2-18b means understanding an entirely new category of worlds. And what we learn here will apply to countless other planets. Because subneptunes aren't rare. They're everywhere we look. They're the most common type of planet in the galaxy. Kepler's data changed everything. Before that mission, we thought planets came in two basic sizes: small and rocky like Earth, or large and gaseous like Jupiter. The survey revealed something else entirely: a population peak between those extremes. Worlds that shouldn't exist according to our solar system's template. They're called subneptunes. Planets ranging from about 1.5 to 4 times Earth's radius. They make up roughly 30 to 50% of all exoplanets we've discovered. Yet we have nothing like them orbiting our sun. It's as if nature's most common planetary configuration somehow skipped us entirely. Or we're the anomaly. This gap in our understanding creates a fundamental problem. When we look at K2-18b, we're not comparing it to anything familiar. We're building models from scratch, testing hypotheses against worlds we've never seen up close. The formation pathways for subneptunes remain contested. One theory suggests they start as rocky cores that accumulate thick hydrogen atmospheres from the protoplanetary disk, born with those massive gas envelopes already in place. Another model proposes they begin as ice-rich bodies that migrate inward. The ice melts under increased stellar radiation. What remains is a water-rich interior beneath a hydrogen atmosphere captured from the disk or outgassed from the planet itself. Both scenarios can produce the same observational signature. Same size. Same density. Same atmospheric composition when viewed from 124 light-years away. But the internal structure would be completely different. One path gives you a rocky world with a thick atmosphere. The other gives you an ocean with a sky. Determining which is correct requires information we don't have. We can't measure K2-18b's internal structure directly. Can't drill into it. Can't send seismic waves through it. We're limited to surface observations, atmospheric analysis, indirect inference. The bimodality in planetary sizes adds another layer to this puzzle. Kepler found that planets cluster around two distinct radii. One group peaks at about 1.3 times Earth's size, the other around 2.4 times. There's a gap between them, a radius valley where fewer planets exist. This suggests different evolutionary paths. The smaller group likely represents rocky worlds that lost their atmospheres, stripped away by stellar radiation over billions of years. The larger group retained their gas envelopes. They're the subneptunes, massive enough to hold on to hydrogen despite their star's influence. K2-18b sits right in that larger cluster. But here's what makes this complicated. The radius valley isn't a hard boundary. It's statistical. Plenty of planets exist in the gap. And the position of that valley depends on the star's properties. Hotter stars push it to larger radii. Cooler stars like K2-18 shift it smaller. Which means K2-18b might be right on the edge of atmospheric retention. Balance between keeping its hydrogen envelope and losing it to space. That position matters for habitability. If the planet is losing its atmosphere, then any surface conditions we observe are temporary. The ocean, if it exists, would eventually be exposed to space, stripped away by stellar wind. The hydrogen atmosphere acts as a protective blanket. But if that blanket is thinning, the clock is ticking. We can estimate atmospheric loss rates, but the calculations depend on variables we can't measure precisely. The star's activity level over time. The strength of K2-18b's magnetic field. The exact composition of the upper atmosphere. Small changes in any of those factors alter the timeline dramatically. Then there's the composition uncertainty. The term subneptune implies a Neptune-like structure. But Neptune is an ice giant. Its interior is thought to contain water, methane, and ammonia ices mixed with rock, wrapped in a hydrogen-helium atmosphere. If K2-18b follows that template, it's not a water world at all. It's an ice world. The water would be high-pressure exotic ices. Not liquid. Not an ocean. Just crystalline structures formed under extreme pressure and temperature. Nothing life could use. The alternative is that subneptunes represent a different category entirely. Not scaled-down Neptunes, but something new. A hybrid between rocky planets and gas giants. With internal structures unlike anything in our solar system. If that's true, then the name itself is misleading. We're calling them subneptunes because we lack better terminology. But they might have more in common with super-Earths than with Neptune. The boundary between those categories is blurry. Super-Earths are typically defined as rocky planets up to about 10 Earth masses. Subneptunes as planets with significant hydrogen atmospheres. But a super-Earth with a thick atmosphere could look identical to a small subneptune. Same mass. Same radius. Same density. The only difference would be internal. One has a thin atmosphere over solid rock. The other has a deep atmosphere with no clear surface. K2-18b's mass is 8.63 times Earth's. That puts it at the upper end of super-Earths and the lower end of subneptunes. Right in the transition zone. Which category it belongs to depends on atmospheric mass fraction. How much of the planet is atmosphere versus core? Current estimates suggest K2-18b's atmosphere could be anywhere from 1 to 10% of its total mass. If it's 1%, the planet is mostly rocky with a substantial but not dominant atmosphere. If it's 10%, the atmosphere is so massive it determines the planet's entire structure. That's an order of magnitude uncertainty. And it changes everything about what the planet is like. A 1% atmosphere means there could be a solid or liquid surface beneath. A place where chemistry happens. Where molecules interact. Where, theoretically, life could exist. A 10% atmosphere means the hydrogen layer is so thick and so hot at depth that no surface exists. Just an increasingly dense gas transitioning into supercritical fluids. No boundary. No ocean. Nothing you could call a surface. Recent modeling work has tried to narrow this range. Simulations of subneptune formation suggest that if K2-18b formed in place, its atmosphere should be relatively thin. A few percent at most. But if it formed farther out and migrated inward, it could have captured much more gas. Migration is common. Most exoplanets we've found don't orbit where they formed. They move. Drift inward through gravitational interactions with the protoplanetary disk or with other planets. If K2-18b migrated, its current position tells us nothing about its formation environment. It could have started beyond the snow line where ice is stable. Accumulated a massive atmosphere in the cold outer disk. Then spiraled inward over millions of years. Or it could have formed roughly where it is now. Never migrated far. Retained only a modest atmosphere. Both histories are possible. Both fit the data. The migration question ties directly to composition. Planets that form beyond the snow line should be ice-rich. Water ice, methane ice, ammonia ice. When they migrate inward, that ice heats up. Some of it melts. Some of it vaporizes into the atmosphere. The result is a planet with a water-rich interior and an atmosphere loaded with volatiles. Exactly what you'd expect from a Hycean world. But planets that form inside the snow line would be rock and metal. Drier. Less volatile-rich. Their atmospheres would be captured hydrogen from the disk. Not outgassed water. The composition would be different. So finding water vapor in K2-18b's atmosphere seems to support the migration scenario. Water got there somehow. Either the planet formed with it, or it was delivered later by impacts. But here's the catch. The water vapor concentration is surprisingly low. Less than 0.1% based on Webb's observations. That's not what you'd expect from a planet with a massive water ocean. Earth's atmosphere is about 0.4% water vapor on average. More in the tropics. Less near the poles. But it's detectable. Measurable. On K2-18b, the water vapor signal is weak. Almost suspiciously weak for a supposed water world. One explanation is the cold trap effect. In Earth's atmosphere, water vapor rises until it reaches the cold upper layers. There it freezes out. Forms clouds. Falls back down as precipitation. This creates a cold trap that limits how much water vapor reaches the stratosphere. K2-18b might have an extremely efficient cold trap. Water evaporates from the ocean below. Rises through the hydrogen atmosphere. Hits a cold layer. Freezes. Never makes it to the upper atmosphere where we can detect it. If that's true, the low water vapor signal doesn't mean there's no ocean. It means the ocean is hidden. Locked beneath a thick atmospheric cold trap. Webb is seeing the dry stratosphere. Not the wet layers below. But that interpretation requires the ocean to exist in the first place. And the competing model suggests it doesn't. That K2-18b is a gas-rich mini-Neptune. The methane we see comes from chemistry, not life. The carbon dioxide comes from the star's radiation breaking apart molecules. The water vapor is just trace amounts, left over from formation or delivered by comets. No ocean required. Both models explain the observations. Neither can be ruled out yet. That's the frustrating reality of exoplanet science. We're working with incomplete information. Building castles on uncertain foundations. And K2-18b is just the beginning. There are thousands more subneptunes waiting to be studied. Each one a mystery wrapped in hydrogen and speculation. The real challenge isn't just figuring out what K2-18b is. It's understanding what subneptunes as a class can actually become. Because K2-18b isn't alone out there. Subneptunes are the most common type of planet we've found. They outnumber everything else. Hot Jupiters, super-Earths, Neptune analogs. Subneptunes dominate the census. Kepler found them everywhere. TESS keeps finding more. They orbit red dwarfs, sun-like stars, even slightly hotter F-type stars. And yet we have nothing like them in our own solar system. Earth is too small. Neptune is too big. There's a gap where sub-Neptunes should be. That gap tells us something important. Our solar system might not be typical. The architecture we're used to, rocky planets close in, gas giants farther out, might be the exception rather than the rule. Sub-Neptunes suggest a different kind of planetary system. One where migration is common. Where atmospheres are thick. Where the boundary between rocky and gaseous isn't clear-cut. Understanding sub-Neptunes means understanding how most planetary systems actually work. And that starts with a basic question. What determines whether a sub-Neptune becomes a Hycean world or stays a mini-Neptune? Size matters. But not in the way you'd think. It's not just about radius or mass. It's about the ratio between the core and the atmosphere. A planet with a large rocky core and a thin atmosphere behaves differently from one with a small core and a massive hydrogen envelope. The core provides gravity, holds the atmosphere down, keeps it from escaping. But if the atmosphere is too thick, the pressure at the base becomes extreme. Temperatures rise. The boundary between atmosphere and surface blurs. You end up with a supercritical fluid. Not quite gas, not quite liquid. Something in between. That's the problem with assuming K2-18b has a solid surface beneath its hydrogen envelope. The pressure might be too high. The temperature might be too extreme. The ocean, if it exists, might not sit on a rocky crust like Earth's oceans do. It could be suspended within layers of supercritical water. Compressed hydrogen above. Dense metallic core below. No clear boundary anywhere. Atmospheric escape changes everything. Hydrogen is light. Really light. It doesn't take much energy to strip it away. Ultraviolet radiation from the host star can do it. Stellar winds can do it. Even the planet's own heat can cause the upper atmosphere to expand and bleed off into space. This process is called hydrodynamic escape. It's why Earth doesn't have a thick hydrogen atmosphere anymore. We lost it early in our history. The sun's radiation stripped it away. Left us with nitrogen and oxygen. Secondary atmosphere formed by volcanic outgassing and later by life. Sub-Neptunes around red dwarfs face a different challenge. Red dwarfs are dim. They don't put out as much total energy as the sun. But they're violent. Especially when they're young. Stellar flares, coronal mass ejections, intense X-ray and ultraviolet bursts. All of that hammers planets in the habitable zone. K2-18 is about 2.4 billion years old. Not particularly young. But not ancient either. It still flares. Still produces bursts of high-energy radiation. Those bursts can strip away hydrogen, peel back the outer layers of the atmosphere. Over time, a mini-Neptune could lose enough hydrogen to become a super-Earth. The core remains. The ocean, if there was one, might survive. But the thick hydrogen envelope is gone. This process might explain why some sub-Neptunes have thick atmospheres and others don't. It's not just about formation. It's about survival. Here's where things get tricky. If K2-18b is losing hydrogen, how much has it lost already? And how much will it lose in the future? Models suggest that planets around red dwarfs can lose significant fractions of their atmospheres over billions of years. But the rate depends on distance from the star. K2-18b is far enough out that the radiation isn't catastrophic. Close enough that it's not negligible. The balance is delicate. If the planet formed with a massive hydrogen envelope, it might have enough left to maintain the Hycean scenario. If it started with less, the envelope might be thinning, transitioning towards something more Earth-like, or maybe something entirely different. A world with a thin hydrogen layer over a high-pressure steam atmosphere. Neither Hycean nor mini-Neptune. Something new. The methane abundance complicates this picture even further. Methane and hydrogen don't normally coexist in equilibrium. At high temperatures, methane breaks down. Carbon and hydrogen separate. You end up with carbon dioxide and water instead. But K2-18b's atmosphere shows both methane and carbon dioxide. That suggests the atmosphere isn't in equilibrium. Chemical reactions are happening. Slowly. Continuously. Methane is being produced somewhere. Either by geological processes on the surface, if there is a surface. Or by life, if there is life. Or by photochemistry in the upper atmosphere, driven by starlight. Photochemistry can do strange things. Ultraviolet light breaks molecules apart. Creates reactive fragments. Those fragments recombine in unexpected ways. On Titan, Saturn's largest moon, photochemistry produces complex organic molecules. Tholins, long-chain hydrocarbons, even amino acid precursors. All without biology. Just chemistry and sunlight. K2-18b's atmosphere might be doing something similar. Starlight hits the upper layers. Breaks apart carbon dioxide and water vapor. Creates methane and other organics. The methane we detect isn't proof of life. It's proof of chemistry. Active, ongoing chemistry. But chemistry that could, under the right conditions, lead to biology. Let's talk about that possibility. Life on K2-18b. Not intelligent life. Not civilizations. Just microbes. Simple organisms. Floating in the atmosphere or swimming in the ocean below. If the ocean exists. On Earth, life appeared relatively quickly. Within a few 100 million years of the planet cooling enough to have liquid water. The early Earth was hostile. Volcanic. Bombarded by asteroids. No oxygen in the atmosphere. And yet life took hold. Adapted. Thrived. If life can start on Earth under those conditions, why not on K2-18b? The planet receives similar amounts of starlight. It's in the habitable zone. Temperatures, at least in some layers, might be right. Water is present, even if only as vapor. Carbon dioxide and methane provide building blocks. The hydrogen atmosphere might even help. Hydrogen can act as a reducing agent. Drives certain chemical reactions that produce organic molecules. Early Earth had more hydrogen in its atmosphere than it does now. That might have been important for the origin of life. But there's a problem. Nitrogen. Life as we know it requires nitrogen. Proteins, DNA, RNA, all contain nitrogen. On Earth, nitrogen makes up 78% of the atmosphere. It's abundant. Available. Organisms have evolved to use it. On K2-18b, nitrogen is conspicuously absent. Chemical models suggest nitrogen compounds would be rare. Hard to detect. The atmosphere is hydrogen-dominated. Hydrogen reacts with nitrogen. Forms ammonia. Ammonia is reactive. Breaks down easily. Doesn't accumulate. Without nitrogen, how does life build proteins? How does it store genetic information? Maybe it doesn't. Maybe life on K2-18b, if it exists, uses a different biochemistry. Silicon instead of carbon. Sulfur instead of nitrogen. Entirely different molecular structures. We don't know if that's possible. We've never seen it. But the universe is vast. Chemistry is flexible. What seems impossible might just be unfamiliar. Then there's the question of energy. Life needs energy. On Earth, most life gets it from sunlight, directly or indirectly. Photosynthesis captures light, converts it to chemical energy. Food chains build from there. But K2-18b's atmosphere is thick. Hydrogen scatters light. Clouds and hazes block it. How much sunlight actually reaches the surface? Or the ocean? If there's an ocean, calculations suggest light levels would be low. Dim. Not zero, but not abundant. Photosynthesis might struggle. Life would need to adapt. Use longer wavelengths. Red light, infrared. Or rely on chemical energy instead. Hydrothermal vents on the ocean floor, if there is a floor, could provide energy. Chemical gradients. Dissolved minerals. Life could cluster around those vents. Just like it does on Earth in the deep ocean. Far from sunlight. Thriving on chemistry alone. That kind of life wouldn't produce oxygen. Wouldn't change the atmosphere. Wouldn't leave obvious biosignatures. It would be invisible to our telescopes. Hidden beneath kilometers of hydrogen and water. We'd never know it was there unless we sent a probe. And even then, finding it would be hard. Life in the deep ocean is sparse. Scattered. Easy to miss. This brings us back to dimethyl sulfide. The controversial biosignature. The molecule that might or might not be there. On Earth, DMS comes from phytoplankton. Tiny marine organisms. They produce it as a byproduct of their metabolism. It escapes into the atmosphere. We can measure it. Use it to track biological activity in the oceans. Finding DMS on K2-18b would be huge. Direct evidence of life. A smoking gun. But the signal is weak. Tentative. Barely above the noise. And there are alternative explanations. Photochemistry. Geological processes. Comets. Even measurement error. The signal could be real but not biological. Or it could be an artifact. Something in the data that looks like DMS but isn't. Distinguishing between these possibilities requires better data. More observations. higher precision. And that means waiting for Webb to observe K2-18b again, for future telescopes to come online, for technology to improve. Science moves slowly, especially when the stakes are this high. But here's what makes the wait so difficult. Every month that passes is a month we could be getting answers. Every telescope hour allocated to other targets is an hour not spent on K2-18b. And the competition is fierce. Webb is the most in-demand telescope in history. Thousands of proposals. Hundreds of targets. Everyone wants time. Everyone has questions that need answering. K2-18b is important, but so are distant galaxies, forming stars, other exoplanets. The telescope can only look at one thing at a time, so we wait. Meanwhile, the debate intensifies. Papers published. Rebuttals written. Models refined. Each new analysis shifts the probability slightly. Sometimes toward life. Sometimes away from it. The scientific process grinding forward at its characteristic pace. Methodical. Careful. Frustratingly slow when you want a definitive answer right now. But this is how science works. How it has to work. Extraordinary claims require extraordinary evidence. And we're not there yet. What we do have is context. K2-18b isn't the only subneptune we've found. There are hundreds. Maybe thousands. Most haven't been studied in detail. Most never will be. Too faint. Too far. Wrong geometry for transits. But they exist. A whole population of worlds between Earth and Neptune in size. And we don't really understand them. Our solar system doesn't have anything like this. Nothing between Earth's radius and Neptune's. No intermediate examples to study up close. So we're learning from scratch. Building models. Testing hypotheses. Figuring out what these worlds actually are. The term subneptune is almost misleading. It suggests a smaller version of Neptune. A mini ice giant. But that might not be accurate. Some could be ocean worlds. Others might be rocky planets with thick atmospheres. Some could have hydrogen envelopes sitting on top of molten surfaces. Magma oceans underneath, not liquid water. The possibilities are broad. Too broad. We need more data to narrow them down. And K2-18b, because it's bright enough to study, becomes a test case. A prototype. If we can figure out what it is, we might understand the whole population. That's why the stakes are so high. This isn't just about one planet. It's about an entire class. Understanding K2-18b means understanding thousands of other worlds we'll discover in the coming decades. Some closer. Some in better positions for study. Some around quieter stars. K2-18b might not be the best candidate for life. But it's the first one we can actually characterize. The first one where we can measure atmospheric composition in detail. That makes it invaluable. Even if the answer turns out to be disappointing. And disappointing is still possible. Likely, even. Most planets aren't habitable. Most don't have life. The universe is vast, but it's also mostly empty. Mostly hostile. Finding even microbial life on another world would be the discovery of the millennium. Maybe of human history. But it's not guaranteed. Not even probable, depending on who you ask. The odds are uncertain. The universe hasn't told us yet how common life is. K2-18b could be the first clue. Or it could be another dead end. Consider what we're actually looking for. Not cities. Not technology. Not intelligence. Just chemistry. Molecules that shouldn't be there unless something is producing them. Something alive. On Earth, that's oxygen. Methane combined with oxygen. Certain gases that react quickly and disappear unless constantly replenished. Biosignatures. But they're not foolproof. Nature is clever. Abiotic processes can mimic biology. Volcanoes produce gases. Lightning creates compounds. Photochemistry, the interaction of light with molecules, can generate complex chemistry without any life involved. Distinguishing between biological and non-biological sources is hard. Sometimes impossible without visiting the planet directly. That's the limitation we're up against. We can study atmospheres from 124 light-years away. Incredible. Revolutionary. But there's only so much we can learn from a distance. We can measure what's there. But understanding why it's there, what's producing it, that's harder. Requires models. Assumptions. Educated guesses. And those can be wrong. Have been wrong before. Will be wrong again. Science corrects itself over time. But in the moment, uncertainty dominates. So what happens next? More observations. That's certain. Webb will observe K2-18b again. Has to. The question is too important to leave hanging. But scheduling is complex. Coordinating telescope time takes years. Planning observations. Analyzing data. Writing papers. More years. We might not have definitive answers for another decade. Maybe longer. That's the reality of astronomy. Progress measured in years, not weeks. Patience isn't optional. It's required. But there's reason for optimism too. Technology improves. Future telescopes are coming. Larger mirrors. Better instruments. More sensitive detectors. The extremely large telescope. The Habitable Worlds Observatory. Missions specifically designed to study planets like K2-18b. They'll see things Webb can't. Measure molecules at lower concentrations. Distinguish between different sources more effectively. Build better models of what these worlds actually look like. And there's another approach. Direct imaging. Instead of watching planets transit their stars, just photograph them directly. Block out the star's light. Image the planet itself. Incredibly difficult. Requires advanced technology. Adaptive optics. Coronagraphs. Star shades. but it's being developed, tested. In a few decades, we might be able to take actual pictures of planets like K2-18b. See their surfaces, if they have surfaces. Watch their weather. Map their features. That would change everything. For now, though, we're limited to spectroscopy. Reading the rainbow. Decoding the light that filters through alien air. It's indirect, but it works. We've learned more about exoplanet atmospheres in the past 5 years than in the entire previous history of astronomy. And it's accelerating. Each new observation teaches us something. Each planet studied adds to the picture. K2-18b is part of that larger story. One chapter in a book we're still writing. And maybe that's the real point. Not whether K2-18b has life right now, but what it represents. The beginning of a new era, when we can actually study other worlds in detail, characterize their atmospheres, ask meaningful questions about habitability, about life, about our place in the universe. For most of human history, those were philosophical questions. Abstract, unanswerable. Now they're scientific questions. Testable. With data. With evidence. That's profound. Whether K2-18b itself is inhabited or not, the fact that we can ask the question, that we have tools to investigate, that's the real breakthrough. Because K2-18b won't be the last. There will be others. Better candidates. Closer stars. More favorable conditions. Planets around sun-like stars instead of red dwarfs. Worlds with oxygen-rich atmospheres. Clearer biosignatures. Less ambiguity. K2-18b is just the first we've been able to study seriously. The first where the technology caught up with the ambition. It's a pioneer. And pioneers are messy. Complicated. Full of contradictions and uncertainty. But they open the path. They show what's possible. They teach us what questions to ask and how to answer them. That's K2-18b's role. Not to give us easy answers, but to show us where to look next. And pioneers teach us what we got wrong. That's crucial. Because K2-18b revealed something uncomfortable. Our models weren't good enough. The planet defied easy categorization. Water world. Maybe. Mini Neptune. Possibly. Something else entirely. Can't rule it out. The data fit multiple scenarios. That's the problem. Or rather, that's the lesson. Before K2-18b, scientists had theoretical models. Predictions about what these planets might be like. How thick their atmospheres were. What molecules they'd contain. How heat would distribute across their surfaces. Then Webb looked. And the reality was messier than the theory. More complicated. The methane levels were higher than expected. The carbon dioxide signal weaker. The temperature structure didn't match predictions. It forced a reckoning. Not with the planet, but with the models. They needed updating. Refinement. More variables. Better physics. That's how science actually works. Not smooth and linear. Messy and iterative. You think you understand something. Then you measure it. And you are partly right and partly wrong. So you adjust. Build better models. Test them. Repeat. K2-18b is driving that cycle now, forcing researchers to confront assumptions about how hydrogen atmospheres behave, how carbon cycles through these worlds, what makes a planet habitable versus just temperate. These aren't small questions. They're fundamental. And they affect how we interpret every other planet we study. Because K2-18b isn't unique. It's typical. Subneptunes are everywhere. Most common planet type in the galaxy. We don't have any in our solar system. Nothing between Earth and Neptune. That gap in size. So we're learning about them from scratch. No local examples to study up close. Just distant observations. Light filtered through alien air. And K2-18b is the best example we have so far. Close enough to study. Bright enough star. Favorable geometry. Regular transits. It checks the boxes. That's why it matters so much. Not because it definitely has life, but because it's teachable. A planet we can actually learn from. And what it's teaching is humility. The universe is more complex than our models. Always has been. Always will be. That's not a failure. It's the nature of discovery. You start with simple ideas. Basic physics. Clean predictions. Then reality shows up. And it's complicated. Full of edge cases. Unexpected interactions. Chemistry you didn't account for. Physics you oversimplified. So you adapt. That's the process. And K2-18b is accelerating it. Each observation adds data. Constraints. Things the planet can't be. Things it might be. Slowly, the possibilities narrow. Not to a single answer. Not yet. But toward better questions. More refined hypotheses. Testable predictions. That's progress. Even when it feels slow. Even when headlines oversell the findings. Even when the public wants simple answers and scientists can only offer complex probabilities. The truth is, K2-18b is forcing us to develop new tools. Not just instruments. Conceptual tools. Ways of thinking about planets that don't fit Earth's mold. Because for centuries, we only knew one planet with life. Ours. So naturally, we looked for Earth twins. Similar size. Similar composition. Similar star. That made sense. Start with what you know. But K2-18b isn't an Earth twin. Not even close. 8 times the mass. Hydrogen atmosphere. Orbiting a red dwarf. Everything's different. Yet it might still be habitable. Might. That possibility is reshaping the field, expanding what we look for, how we define habitability. Because if life can exist there, under those conditions, then the range of possibilities is much wider than we thought. More planets qualify, more systems to study, more chances to find something. But here's the thing. We still don't know if K2-18b itself qualifies. The jury's still out, and might be for years. Because this isn't a simple measurement. It's an interpretation problem. The data is real. The spectra are accurate. But what they mean depends on context we don't fully have. Temperature profile of the atmosphere. Unknown. Circulation patterns. Unknown. Cloud coverage. Unknown. Surface conditions, if there even is a surface. Unknown. We're trying to solve a puzzle with most pieces missing. And some pieces might not even belong to this puzzle. They might be contamination, noise, artifacts of how we process the data. That's always a risk, especially with signals at the edge of detectability. You see a pattern. Is it real? Or is it statistical fluctuation? Free sigma confidence sounds impressive. Until you remember that means 1 in 370 chance it's random.